Hello everyone. Welcome to grade 11 physical sciences revision. This is for term 3. So today I took a question paper from the Limpopo province. It was a district question paper for Mopani East District. It was a controlled test 2 for September 2023. So that's the question paper that I want us to use for our revision. The question paper was out of 100 marks and it was supposed to be written in 2 hours. So let's use this question paper, good people, to guide ourselves as we prepare for our September term 3 exams. So our question paper was actually into 2 parts. We've got the multiple choice questions and then we've got the structured or else the open-ended questions. The multiple choice questions, there are only 5, and then we have also 5 other questions. Now let's get started. For the multiple choice questions, we know that good people would be having 4 options. It's either you have A, B, C, or D, and there is always only one correct answer. There are not more than one. There is always one correct answer. So we need to choose carefully the most accurate answer. That's the one that we get to take. So let's see what question number 1.1 was saying. If the pressure on a 100 grams of an enclosed nitrogen gas is doubled and the temperature is kept constant, the average speed of the nitrogen gas molecules will what? Are they going to double? Are they going to be 4 times greater? Are they going to be 4 times smaller? Are they going to remain the same? So what is the concept that is being asked here? They want us to actually get to determine the relationship between the pressure, the temperature, and the average speed of the gas particles. So from our kinetic theory of matter, or else the kinetic theory of gases, it tells us that we are able to define our temperature as the average kinetic energy of what? Of our gas particles. So our temperature can be the average, or else it can be the measure of that average kinetic what? Average kinetic energy. So we know that the higher our temperature within our system, the higher the average kinetic energy of what? Of our gas particles. Now here they are telling us that the temperature is kept constant. So once our temperature is constant, it simply means that our average kinetic energy is also going to remain what? Constant. So what is the relationship between the kinetic energy of a gas particle and its speed? We know that kinetic energy is given by half mv squared. So we can see that the kinetic energy is directly proportional to the what? To the speed of our gas particles. So once the kinetic energy remains constant, our speed is also going to what? To remain constant. So the speed, or else the average speed of the nitrogen gas molecules, is going to remain constant. So the option that was accurate there was supposed to be what? D. Let's go to 1.2. They are now saying that on 1.2, let me just bring it up so that we can see the whole question. I would also get to just make question number 1.3 visible as well. Now, 1.3 was saying, 1.2, sorry, the correct formula for nitric acid is what? We need to know the correct formulas for our common acids. For example, for nitric acid, we know that it's HNO3. This we should know. So the answer here was supposed to be C. And then this one, it's sulfuric acid. Then this one, it's it's acetic acid, which we refer to as vinegar. And then this one is ammonia. So we are supposed to know the common formulas for our common acids as well as bases. Just like for sodium hydroxide, potassium hydroxide, we need to know these formulas because they are part of our syllabus. So the answer for 1.2 there was supposed to be C. Now let's go to 1.3. 1.3 is saying, consider the following acid-base reactions, which is for ammonia and water to give us ammonium ions and hydroxide ions, and then sulfate plus nitric acid to give us hydrogen sulfide as well as nitrate. So now they are saying the substances acting as proton acceptors in the above reactions are. So we need to determine proton acceptors above here. So proton acceptors, they receive an H plus and then they get to add within their compound this H plus. These are what we refer to as Bromstead bases, or else Bromstead-Lowry theory bases. So here we have got ammonia, it was having NH3, and then now it is now ammonium, it is now having NH4. So we can see that this one, it is actually a proton acceptor. We have sulphate here, and then at the end it is hydrogen sulfide, so it received this H. So sulfite is also a proton acceptor. So our proton acceptors were ammonia and sulfide. So our answer there was just supposed to be B. So let's go to 1.4. 1.4 was saying ozone decomposes to form oxygen gas according to the equation. 2 moles of oxygen, 2 moles of ozone decomposes to form 3 moles of oxygen gas. Which one of the following is not correct? So which one is not correct about the equation of the reaction? So we are saying, according to the equation, 2 moles of ozone decompose to produce 3 moles of oxygen. Yes, according to that reaction, 2 moles of ozone are decomposing to form 3 moles of oxygen gas. This is true. And then 2 grams of ozone decompose to produce 3 grams of ozone, 3 grams of oxygen. This is not true. Why? Because we are saying that you can see that the atomic mass of oxygen is the same. So if we try to actually get to find the molecular mass this side, it is going to be what? 2 times 3, it is going to be 6 times 16. And then the molecular mass this side as well, it will be 6 times 16. So in terms of the number of grams that are going to be formed, which is of oxygen, they are going to be equivalent to the number of grams that we have for oxygen, because we are saying that we do what we call a mass balance. The mass that entered is the mass that we should receive at the end. So if we are going to have 2 grams of ozone decomposing, we are supposed to also form 2 grams of what? Of oxygen. So this is incorrect. So our answer there was supposed to be B. And then let's just go to option C and D. 96 grams of ozone decomposed to produce 96 grams of oxygen. This is true because if you say 6 times 16, you are going to get 96. If you say 6 times 6, you are going to get 96. And then 1.204 times 10 to the power 24 molecules of ozone decomposed to produce 1.806 times 10 to the power 24 molecules of oxygen. So we use our mole ratio to determine this number of what? Of molecules. So you can see that the mole ratio there for oxygen, or else for ozone as to oxygen, it's actually what? 2 as to 3. So is this number of particles, their ratio equivalent to 2 as to 3? If you say 1.204 divided by 1.806, yes, you are going to get 2 over 3. So the option which is not correct there is B. So our answer for 1.4 was supposed to be B. Now let's go to 1.5. The question is saying, let me just wrap this. The question is saying the mass of 0.2 mole of bromine would be, what would be the mass? We know that number of moles is given by the mass of the substance divided by its molar mass. So the mass of bromine there, bromine, it's a molecule, so it's Br2. It will be equal to the number of moles times the molar mass of bromine. So we need to find the molar mass of bromine. So how do we find the molar mass of bromine? We actually need to find the atomic mass of bromine from the what? From the periodic table. So now we need to actually go to our periodic table. So I have a periodic table here with us, and then we can see that Br, its atomic mass is 8. So if I multiply by 2, it will be 160. So for Br2, which is bromine, it will be equal to 160. So now let's return to our question and let's get to see what they are saying. So from our question, they want us to find the mass of what? Of bromine. So they want us to find the mass of bromine. So we say the number of moles times the what? The molecular mass, which is 160. So the number of moles, it's 0.2 times 160. What is 0.2 times 160? 0.2 times 160. Using my calculator, I'm finding what? 32 grams. So let's just get to punch our calculators and confirm that. So here we are supposed to find an answer which is equivalent to 32 grams, or else approximately equal to 32 grams. So we can see that from the answer that we have, something that is more accurate would be 31.96 grams. So our answer was going to be A, because if you round off 39.6, it is going to give you 32. And there is nothing else that is more close to what? To 32 grams other than this. So the answer there was just supposed to be A. Now let's go to our section B, which is just our structured questions. Now we have got question number 2. Let's look at question number 2 and actually get to see what is it that we are given and what is it that we need to find. So question number 2 is saying a chemical substance consists of 85.71% carbon, 14.29% hydrogen. The molecular mass of the substance is 42 grams per mole. Determine the empirical formula for the substance. So how do we determine the empirical formula? I usually advise that people use a table. It becomes easier. So let me just move this aside so that I can draw that table here, and then we determine the empirical formula. So you draw your table just like this. So your table would actually get to consist of, we need to name the elements that we have on our compound. And then we need to actually get to determine the basis of our mass. So we are going to assume to say, let's say we have got 100 grams of our what? Of our compound. And then now with that basis, we'll be able to find the mass of each element that we'll be having. So what are the elements that we are having here? The elements, we have got carbon, and then we have got hydrogen. And then thereafter, we need to determine the mass of each element using this mass composition that we are given. So they are saying 85.71% of carbon. So if we are having 100 grams of compound, it simply means that the mass of carbon is just going to be equivalent to this percentage, which is just going to be equal to what? 85.71 grams. And then the mass of hydrogen is going to be equal to 14.29 grams. And then after that, we need to determine the number of moles of each. So we are going to say mass divided by the molar mass. So the mass here for carbon, it's 85.71 divided by the molar mass of carbon. The molar mass of carbon, we all know that it's 12. The atomic mass of carbon is 12. And then the atomic mass of hydrogen there is 1. So here we are going to divide by 12, and then we get to get our number of moles. So if we get to say 85.71 divided by 12, using my calculator, I'm finding 7.1425. So let's get to cross-check with our calculators, 7.1425. So those are the number of moles for carbon in this compound. If we are using a basis of 100 grams with this mass composition. Now let's go to hydrogen. If I say 14.29 divided by 1, which is the atomic mass of hydrogen, I'm just going to get what? 14.29. Now I need to determine the simplest the simplest mole ratio that I can get between these two. So how do I find that simplest ratio? I need to divide by the smallest number of moles. So by dividing by the smallest number of moles, I can see that the smallest number of moles, it is that for carbon, which is just 7.1425, because this one is smaller than 14. So if I divide this by 7.1425, I'm going to get 1. And then if I divide this 14.29 by that smallest number, which is 7.1425, if I punch my calculator, the approximate whole number that I'm going to get there, it's going to be 2. So the simplest whole number ratio would be just CH2. That becomes our empirical formula, because we know that empirical formula simply means the simplest whole number ratio of the atoms in our what? In our compound. So this becomes our empirical formula. So that is how you were supposed to determine your empirical formula. By simply using that table, you were just going to do that in a simpler way. Now determine the molecular formula of the substance. Now, given that the empirical formula is CH2, they now want us to determine the what? The molecular formula, given that the molecular mass is 42 it's 42 gram per mole. So what it simply means is the molecular formula there that we see, it's equivalent to X times the molecular formula of our empirical formula. So what is the molecular formula of this compound that we have in accordance to our simplest ratio? So you would see that this 42 gram per mole would be equal to X times the molecular mass that I'm going to get from this. It will be 12 plus 2, that is going to be what? 14. And then I now need to find X. So X would be equal to, I divide 42 by 14. X would be equal to, if I say 42 divided by 14, I'm actually going to get 3. So after getting 3, it simply means that my molecular formula, which I would represent by M, is simply equal to 3 times the empirical formula that I have. So I'm going to multiply the ratio that I have here on my empirical formula by 3, which is going to say, if I say 1 times 3, it is going to be C3. If I say 2 times 3, it is going to be H6. So this becomes my molecular formula. So for question number 2.2, my molecular formula was going to be C3H6. Now let's go to defining the term limiting reactant. So how do we define limiting reactant? I would actually get to write 2.3 below here. So I would say 2.3. A limiting reactant is that reactant that is going to be completely used up first in our reaction. So we get to say that a limiting reactant is a chemical reactant that gets completely used up first in a chemical reaction. In a chemical reaction. So that is what we refer to as a limiting reactant. The one reactant that you are going to finish first as long as your reaction is still proceeding. So it means that once that reaction has been completed, it simply means that the reaction is now complete. The reaction is going to stop. That's why we call it limiting. It is going to limit the extent to which our reaction is going to go. So the one that gets finished or else used up first, that becomes our limiting reactant. Now 2.4, it is saying, so allow me to just get to wrap this information. If you want to see what we have done, you can pause, or else you can actually get to rewind back. Now let's get to say 16.70 grams of iodine oxide are mixed with 11.2 grams of carbon monoxide and heated to form carbon dioxide and iodine. Now, this is the reaction. And then they are saying determine which reactant is the limiting reactant here. You see now, they said define the limiting reactant. Now they are saying determine the limiting reactant in between that reaction. So what are we saying? We are saying that given the mass that we have for this and the mass that we have for that, using this reaction, we can be able to determine our limiting reactant, in a sense to say we need to determine the number of moles of our carbon, which becomes the number of moles of our reactant 2, and the number of moles of our iodine oxide to determine the number of moles of our reactant 1. And then after determining those number of moles, we get to determine how much this reactant needs of this for it to actually get to what? To react completely, and also determine how much of this needs from this using this moles. The one that requires lesser number of what? Of moles from the other is the one that we refer to as the what? Limiting reactant. So now let's determine the number of moles. So we'd come and say 2.4. We would first determine the number of moles of that compound, which is our first reactant, by saying mass over the molar mass. Now let's go and look for the atomic mass of iodine, because that one is not common. So for iodine, it's 127. And then for oxygen, it's 16. So these are the atomic masses that we use for our molar mass. So let me just get to rub for bromine there. We want the one for iodine and the one for oxygen. So now we now have them. Let's go back to our question so that we can use these atomic masses to actually get to what? To calculate our molecular mass. So here we are given the mass of iodine oxide. It's actually what? 16.70 grams divided by 2 times 127 plus 2 times 16. And then this was supposed to give you, if you punch in your calculator, you are supposed to get the number of moles there was actually supposed to be equal to 0.06 moles. Mind you, I rounded off here. It was 0.05. It was 0.058 something. So I just rounded, or else let me just get to say, because this one is not our final answer. But in actual essence, we are not looking for numerical values. We want to determine which one is the limiting reactant. So we can just get to round off here. So I just rounded off. So pardon me there. Let's use this value, or else punch in your calculators. You are going to find a value that is approximately equal to this one. Now let's go to the number of moles of carbon monoxide, the mass divided by the molar mass. The mass there for carbon monoxide is 11.2 grams divided, because this one would be in gram per mole. That's the reason why we would have moles here. This one would be divided by 12 plus 18. And that one becomes what? 30. So if you divide by 30 as your gram per mole, you are just supposed to find something like 0.4 moles. Now I have got the number of moles of this, and I have got the number of moles of this. Now, what is the molar ratio in terms of these reactants? Like, how are they reacting? You can see that we have got 1 mole, we have got 1 mole of iodine oxide reacting with 2 moles of carbon monoxide. So the reaction molar ratio is 1:2. So it simply means that iodine will require 2 times of its number of moles from carbon monoxide, whilst carbon monoxide will require half of its number of moles from iodine. So now let's get to see what I'm saying there. So we want to calculate the number of moles required by iodine oxide. So you would actually get to say that for IO2, it requires 2 times of what? Of the number of moles of what? Of carbon monoxide. So the number of moles of iodine required, they are 2 times the number of moles of carbon monoxide required to completely react this would be 2 times of this. So you can see that the number of moles here we said is 0.06. So 0.06 moles of iodine oxide will require 2 times 0.06 moles of carbon monoxide. So this one will certainly require what? It will require 0. If you say 2 times, it will be 0.12 moles. And how much of the carbon monoxide is available? We have got 0.4 moles of carbon monoxide. So we can see that carbon monoxide is sufficient. So we can say, therefore, carbon monoxide is sufficient for what? It is sufficient for the reaction of iodine oxide. Let's now determine the number of moles that are required for the number of moles that we have for what? For carbon monoxide there. So the number of moles that are required for the number of moles that I have there from iodine would be to say I have got 1 there. You can see that I have got 1. So this one would actually require half of its number of moles. So here I would actually get to require what? 1/2 of the number of moles that we have for carbon monoxide. So we are going to say that here I have got 0.4 moles of carbon monoxide. And this will require, for it to completely react, it will require 1/2 of 0.4 moles and of what? Of iodine oxide. And this would be equal to what? If you say half of that, it would be 0.2 moles. And you can see that we do not have enough iodine oxide to react with what? We do not have enough iodine oxide for what? For the reaction with carbon monoxide. So it simply means that our iodine oxide is going to finish up first before what? Before our carbon monoxide. So this one is going to be completely used up first. This one is going to be used up first before our carbon monoxide, because here we have got enough of our carbon monoxide to react with this. So once these total number of moles have reacted, it simply means that the reaction is going to what? Is going to stop. So our limiting reactant there simply becomes our what? It will simply become our iodine oxide. So you would come and say, therefore, iodine oxide becomes the limiting reactant. It becomes the limiting reactant. That is how you determine a limiting reactant. So we're just trying to determine if we have got enough of the what? Of the number of moles of iodine oxide to react with what? With carbon monoxide, given that equation that we are given there. So we saw that iodine oxide is going to be used up first before this one. So this becomes the limiting reactant for our reaction. Now they are saying how many grams of the other reactant are in excess. So since we now know the amount that is required, the amount of our iodine oxide that is going to react, and since this is our limiting reactant, we actually get to limit our reactant to this. So how much of our carbon monoxide is going to react with this, and how much would be left, because this is the only thing that is in excess. So we can just get to go back there on our calculations and get to see how we would calculate the excess. So if I go down, I just want to create space. So we say that the number of moles that we have available, the number of moles of carbon monoxide available, because carbon monoxide is the one that is in excess. The number of carbon monoxide available is equal to what? 0.4 moles. And then the number of moles of carbon monoxide that are going to react, that are required for our reaction, are equal to, we determine them to be 0.12 moles. And then the number of moles of carbon monoxide that are going to remain, that are in excess. Now, for us to find excess, we are going to say the number of moles that are available, which is the total number of moles that we have, minus the ones that are going to react, which are required for our reactions, are going to give us the excess that are going to what? The ones that are going to remain. So the excess is the one that is going to remain. So we are going to say 0.4 mole minus 0.12 mole. And then the difference there is going to be what? If we say 0.4 minus 0.12, we are going to get 0.28 moles. So these are in excess. So these are the number of moles of carbon monoxide that are in excess. But they want us to find the mass of carbon monoxide that is in excess. So how do we find mass? We actually use that relationship which says that number of moles is equal to mass over what? Over molar mass. So we need to determine the molar mass of what? Of carbon monoxide, for which we have determined it already. And then we said it's 12 plus 16, which is 30. So the mass there, it's simply going to be equal to what? Number of moles times the molar mass of that carbon monoxide. So this was going to be equal to, I just get to substitute the values that I have. So my mass was simply going to be equal to 0.28 times my molar mass, which is 30 grams per mole. And then this one was actually going to give me what? If I say 0.28 times 30 grams per mole, I was going to get 7 point. So this one was actually going to give me what? This one was going to, if you say 0.28, I'm just cross-checking that answer, 0.28 times 30 grams, it was going to give you 8.4 grams. You were just supposed to find 8.4 grams. So we are saying that this is 12 plus 16. Oh, sorry, this is 12 plus 16. Here I was saying 30. So this is just supposed to be 28. So I can see that this was supposed to be 28. So that if you say 12 plus 16, it is actually going to be 28 grams per mole. That is the molar mass of what? Of carbon monoxide. So if we use that, it will be 0.28 times 28. And then you are going to get what? You are going to get, if you do that 0.28 times 28, you are getting an answer of 7.84 grams. So that is the mass that is in excess of what? Of carbon dioxide. So that is the carbon dioxide in excess. That is the mass of the carbon dioxide in excess. That is how you calculate that. Now let's go to our following question. So our following question is question number 3. Let's actually get to go through question number 3 and see what is the information that is given and what is it that they want us to find. So question number 3 was saying pure carbon, pure copper. So here it's pure copper sulfate. So pure copper sulfate is a white substance that turns blue in the presence of water. So as long as we have got water, that pure copper sulfate, which is a white solid, becomes blue. Now they are saying the following reaction represents the process. So now they are telling us that there is blue copper sulfate. So this one is hydrated copper sulfate. So in the presence of water, our copper sulfate becomes blue. And they are saying that this hydrated water now gets to dissociate to form our what? They are saying that it forms copper sulfate, a white, and then this hydrated water. So it simply means that here the copper sulfate was heated. So this is what? Heating. It was heated to actually get to vaporize this water so that it becomes dry. Because they told us that as long as it's a what? It's a pure substance. It is white in color. But once there is water, it simply means that there is actually what? The compound is going to be blue. So what we are saying that to remove water, what do? We heat to evaporate. Now they are saying that 49.90 grams blue copper sulfate is heated. Yes, so this one was heated until 31.90 grams pure white copper sulfate remains. So this is what I was just explaining to say that our compound there, it's white in color as long as there is absence of water. But once there are water molecules, our substance actually becomes what? Blue in color. So they are saying that this hydrated copper sulfate was what? Was heated to a white compound which has got what? 31.9 grams from 49.90 grams. So now they're saying, what is the percentage purity of copper sulfate in the initial sample? So the percentage purity, you are just going to say that the original amount or else the total amount of your pure copper that you are having divided by the total of the compound that has got both pure copper and water. So you're just going to say what? The amount that you have, which is 39.0, which is the pure amount divided by the total amount of the compound, which is what? 49.90. Because here we are told that before the hydrated copper sulfate was having a mass of what? 49.90. So they weighed the mass of this and it was 49.90. And then after heating, they weighed the mass of this and it was now 31.9. So it simply means that we have got 31.90 pure white copper sulfate in this total compound. So what is the percentage purity? If you divide here, you now later multiply by 100% so that you can get that percentage purity. So by doing that, you were supposed to find, if you say 31.90 divided by 49.9, you were going to find 63.9. It was going to be 63.9%. So your percentage purity there, it was just supposed to be 63.9%. So we are saying that percentage purity would be equal to 31.9 divided by 49.9 times 100%, because we are looking for percentage, and this was going to give you 63.9. It was 63.93% after rounding off. And then how many moles of copper sulfate is present in the blue copper sulfate? So we now want to find the number of moles of copper sulfate that are present in this blue copper sulfate, in this blue hydrated copper sulfate. How do we find that number of moles? How do we find that number of moles? We simply need to actually get to find, because already we know the total mass. We now need to find this X. After finding this X, we can actually get to find what? The number of moles. But since we already know the pure copper sulfate mass, we can simply use N is equals to mass over molar mass. We can simply use what? Mass over molar mass. So the molar mass of what? Of copper sulphate. What is the molar mass of copper sulphate? What is the molar mass of copper sulphate? We just get to, you have to add the atomic mass for that, and then 16 times of that. Let's go and get the one for copper, because that one is not common. So you can see that for copper, we need to find the one for copper. For copper, it's 63.5. So here it's 63.5. That is for copper. And then we need for copper sulphate. So 63.5 plus for sulfur. Our sulfur, it's 32. The one for sulfur, 32. And our oxygen is 16. We get to say 16 times 4. What is the total there? The total is supposed to be 63.5 plus 32 plus 16 times 4. And then we get 159.5. So the total molar mass there, it will be 159.5 grams per mole. So that is the molar mass that we are going to use, which is for copper sulphate. So having that molar mass, we are given the mass of the pure copper in our substance. So we know the pure mass of our what? Of our white copper sulphate. So that mass is what? 31.90 divided by the molar mass. We said it's 159.5. So our number of moles there, the number of moles, we're just going to be equal to what? You were just going to find, if you say 31.90 divided by 159.5, you are going to find, after rounding, 0.2 moles. So those are the number of moles of what? Of copper sulphate. Because we already know the pure amount that is in here. So there is no need of actually first finding this and later finding the what? The number of, we already know the pure compound here. So we just use that mass divided by its molar mass. Now let's go to calculate the value of X in the reaction. What is the value of X? Now, since we now know the number of moles, of this pure copper sulphate, now we are now able to calculate the number of moles of X. How do we do that? We just get to go and say, here we are given our hydrated compound being 49.90. This is for our hydrated compound, which is what? Copper sulphate XH2O. And we know the one for our pure, which is this one, which is 31.90. And then whatsoever would be left would be for this now. That would be X times the molar mass of what? Of H2O. So for us to find this now, we are now going to say that since we know that 49.90 minus 31.90, it's going to be equal to what? It's going to be equal to X times the one for water, which is just 18. So to actually get to find our what? To actually get to find, so now we need to actually get to find the mass that is equivalent to that. The mass that is equivalent to that is going to be the difference. So the difference there was just going to be 49.90 minus 31.90, and then that becomes equal to 18. So this one is equal to 18 grams. So the mass of our water of crystallization is equal to what? To 18 grams. The total mass of our water of what? Of crystallization. Now, for us to find X, we now need to determine the number of moles of our pure copper sulphate and the number of moles of our what? Of our hydrated water, so that we can actually get to determine the simplest what? Mole ratio there, the simplest atomic ratio. So what we do is you actually get to say that our copper sulphate is going to have its own number of moles due to its mass over molar mass. We already calculated that. And then this hydrated, or else this water of crystallization, which is XH2O, it's also going to have its number of moles, which we are going to calculate from mass over molar mass. So here we are going to say 18 grams divided by the molar mass of the water. That is just 18 grams. So you can see that here I'll be having 1 mole. And then what about the number of moles for copper sulfate? The number of moles for copper sulfate, we determine them to be 0.2 moles. So you can see that the mole ratio here is just what? 1 is to what? Is to 0.2. Now, for us to determine X, we now get to say that X is actually equal to that 1 mole divided by what? 0.2. You are going to find that this is actually going to be equal to what? This was actually going to be equal to 1 divided by 0.2 is equals to 5. So our X there was equal to 5. Now I know that I said a lot of things there, and someone might actually be failing to actually get to follow what I've done. Let me just get to erase this, and then let me try to go back a little bit slower, and then I'll take you through the steps, because now we now know where we are going. And some of you, you now already have a hint of what we are looking for. We are saying that if we were having, let's get to say, if we were having two compounds reacting, we were going to use the mole ratio of this. And then to actually get to what? We would need to actually get to find what we refer to as the empirical formula. The empirical formula is just the simplest ratio of the number of moles in terms of how they are in relation. So just to actually get to illustrate from our previous empirical formula, we said that we were having what? CH2. And we found that CH2, this simplest ratio, we found it by saying that we know the number of moles of carbon and the number of moles of hydrogen. And we said the number of moles of carbon was something like what? It was something like, if I still remember, 7.1425. And then the number of moles of hydrogen were something like 14.29. And we said, let's find the simplest ratio there. And we say that our simplest ratio, we found it by dividing by the lowest number of moles. So if we divide by 7.1425, we're going to find 1 here. If we divide by 7.125 here, we're going to find 2. So that our simplest ratio was just going to be 1:2. That's the same thing that we want to do with our copper sulfate, the hydrated copper sulfate. So we are going to take this maybe as represented by B, and then we are going to take this O as represented by A. So we want to find the simplest mole ratio that we can get from A and B. So we can find that by calculating the number of moles of copper sulfate, given that we know the mass of the pure mass of copper and the molar mass of copper sulfate. So we say that this gave us 0.2 moles. And then we would also want to find the number of moles of our water by saying that the mass of our total compound of this water of crystallization divided by the molar mass of water. And we determined that mass by actually calculating the difference from the total, which was 49.90 minus 31.90. And then this actually gave us a value of what? It gave us a value, if you say 49.9 minus 31.9, it gave us a value of 18. And we say that we have got 18 grams of this. So for us to find the number of moles of that, we were just going to use that 18, and then we were going to divide it by the molar mass of water. The molar mass of water is 18, so we say gram per mole there. We're going to find the mass to be the moles to be 1 mole. So we can see that the total number of moles that we have in this compound are equivalent to 1 mole. The total number of moles of copper sulfate in this compound are equivalent to 0.2 mole. Now, what is the simplest ratio between those two moles? We divide by 0.2 moles. If we divide by 0.2 moles, we are going to get the simplest ratio of this one. If I divide by 0.2 moles, I'm going to get what? If I say 0.2 divided by 0.2, I'm going to get 1. This one, if I say 1 divided by 0.2, I'm going to get what? I'm going to get 5. So our simplest ratio is since we say this is represented by A, this one by B, would be A as to B. So it would be 1 as to 5. So it will be simply what I am representing as A to be copper sulfate times 5 of what I'm having here as H2O, 5. So you can see that instead of bringing this 5 here, I can even bring this 5 here because I'm still multiplying that. So I would be having copper sulfate dot 5 of my what? Of my water. So this is where we are getting to say that the value of X is supposed to be equal to what? To 5. So we are just looking for the simplest mole ratio between these two in our hydrated compound, which is this one. So that is how we're going to find our X. Now let's go back to our questions and let's see the following questions. So allow me to just get to rub through here. So now after finding our X being equal to 5, let's hear the following question. Our X was equal to 5. Now they're saying how many water molecules evaporated? How many water molecules evaporated? Now for me to calculate the number of molecules that evaporated, I would simply need to use N is equal to what? The number of molecules, or else let me say this one, the number of molecules that evaporated divided by the Avogadro's constant. So now for me to find this, let me just get to rub here, because I'm looking for those number of water molecules that evaporated, these ones. I need to use the number of water molecules that evaporated. So I calculated the number of water molecules that evaporated to be the 18 grams of that water divided by 18 grams per mole. And I found out that this was equal to 1 mole. So you would actually get to put 1 mole here. But we know that 1 mole of 1 mole of any compound is equivalent to what? It's equivalent to 6.02 times 10 to the power 23. So the number of water molecules that evaporated, are just equivalent to that Avogadro's constant, because we have got 1 mole of water that evaporated. So I would actually get to say that the number of water molecules that evaporated are just equal to what? 6.022 times 10 to the power 23. Those are the number of water molecules that evaporated. Those are the number of water molecules that what? That evaporated there. So they are just 6 point what? They are just 6.22 times 10, 6.022 times 10 to the power 23. That is how we're going to find our number of water molecules, because we know that 1 mole of water evaporated from the given masses there. Now let's look into our next question. So our next question is about energy and change. So now let's get to look into this. They are saying that the following graph shows a potential energy graph for the reaction of A plus B to form C plus D. So here you would be having your A plus B to form what? To form C plus D. And here you would be having an activated complex of what? Because here at some point in time, I would be having A to form maybe to form C, having B to form D. So your activated complex is when A is actually now beginning to actually wants to form what? C and D. This. So now we get to say that 4.1 is the forward reaction endothermic or exothermic? Motivate your answer. We know that for us to determine endothermic or exothermic, we know that thermic, we know that endo we release, endo we absorb. So our endothermic, we absorb, and then exo, we release. So if we are releasing energy here, it means that our delta H is supposed to be what? It's supposed to be greater than zero. And then if we are releasing energy, our delta H is supposed to be less than what? Zero. What do we mean by that? We know that our change in enthalpy is going to be enthalpy of products minus enthalpy of what? Of reactants. So enthalpy of products, if enthalpy of products is greater than enthalpy of reactants, this is actually going to give us what? If enthalpy of products is greater than enthalpy of reactants, this is going to give us what? An endothermic reaction. If our delta H were HP minus HR, so this is where we get to say HP is greater than what? HR. And this one is actually going to be greater than 0. And then when HP, the enthalpy of products is less than the enthalpy of reactants, it simply means that we released energy. That's the reason why the enthalpy of the products it's less than the enthalpy of the reactants. Let me just get to repeat this again, because this is where almost everyone gets to lose it, to say, why would you say the one that has got negative is equal to endothermic, while least so we are saying that if I have got A plus B to form C plus D, if I'm having an endothermic reaction, I know that these two, they have to absorb energy. So I'm going to say A plus B plus the energy that they are going to absorb. I'm going to give C plus D. So now, when I now want to balance my energy, because I know that energy is neither created nor destroyed. So energy in, we get to say the total energy in should be equal to the total energy out. So I'm going to say that the energy that the enthalpy in should be equal to the enthalpy out. So enthalpy out, you can see that it is only enthalpy of my what? Of my products. This is for an endothermic. And then enthalpy in, you can see that it's enthalpy of my reactants plus the enthalpy of the energy that was what? That was absorbed. So this would be actually H absorbed. H absorbed. So you can simply see that H products is greater than HR, because HR to actually equivalent to H products, we need to add energy. So here HP is actually greater than what? HR. If that is the case, if I now get to find the change in enthalpy by saying HP minus HR, I'm going to get a what? I'm going to get a positive value. So this one is going to be greater than what? 0. So this is for an endothermic reaction. So it simply means that the enthalpy of products would be greater than the enthalpy of reactants for an endothermic reaction. And the opposite would be true for an exothermic reaction. So this one, you can see that your products, this is where you have got HP, is greater than your HR. So since HP is greater than HR, this is endothermic, because we know that at some point in time, your reactants absorbed energy to give us this higher energy of the product. So this equation was what? This reaction was endothermic. That was the answer there. And that is how you actually get to what? to determine if it's endothermic or else it's exothermic. So let me just get to rub there. So in summary, someone would say for endothermic, delta H is greater than 0, means HP would be greater than HR. Enthalpy of products is greater than what? Enthalpy of reactants. And then for exothermic, you come for exothermic. For exothermic, delta H would be less than 0. That means that HP is less than HR. That is how you determine in between the two. And here, this is what we have for HP. This is what we have for HR. So you can see that for our reaction, HP is greater than what? HR. So our reaction is what? It's endothermic. So how do you motivate your answer? You get to say, because HP is greater than what? HR. It's endothermic reaction because enthalpy of products is greater than what? Enthalpy of reactants. That was how we were going to motivate your answer. Once your enthalpy of products is greater than enthalpy of reactants, you know that you would actually get to say, therefore, delta H would be greater than what? 0. We know that delta H greater than 0, it simply means it's what? Endothermic. In scientific terms, we know that. So once you do that, you have answered your question. Now let's go to the following question. Calculate delta H for the forward direction. So delta H for the forward direction was going to be equal to HP, which is 40 kilojoules minus 10 kilojoules. That was going to give you what? 30 kilojoules. And then define the activation complex. So the activation complex is just the unstable temporal arrangement of the what? Of the atoms that form just before atoms start to combine. Like I said initially, I said that you would have in what? You would have an activated complex here. This is a temporal arrangement that you are going to have of atoms of these reactants. Like for example, let's say that we are reacting H plus fluorine to form hydrogen fluoride. The temporal, you would actually see that I have got HH bonds that needs to break as well as FF bonds. So the temporal arrangement, this is the temporal arrangement before the product starts to form. My temporal arrangement here would be for HF and HF. So here I would be having H, and then I would also come and have an F there. So the temporal arrangement would be for these two. So this temporal arrangement of atoms is what we refer to as the activated what? Complex. So let's just get to write the definition neatly there. We get to say that, let me write it below, or else let me try to write it here. Activated complex, activation complex is the unstable temporal arrangement of reacting atoms before uh, before maybe the resulting products form. Product atoms actually form before the resulting product atoms actually form. So that unstable temporal arrangement that you have for your atoms before the product atoms they get to start to form, that is what we refer to as the activated complex. Some they would call it an unstable temporal arrangement of atoms before the actual atom starts to form. So you would either take this definition or else the other one. So we all mean the same thing. That's the reason why I gave an example of what hydrogen reacting with fluoride to form hydrogen fluoride. Now they are saying what is the what? So let me just get to erase this. I'm sure you have copied that definition. Or else let me just get to show it here. So here we are saying what is the energy of the activated complex? Energy of the activated complex from this diagram, the energy of the activated complex would be 60 kilojoules. That is the energy of the activated complex. So the energy of the activated complex there would be 60 kilojoules. That is the answer for 4.2. So 4.4 there would be equal to what? 60 kilojoules. And then now they are saying define the activation energy. We know that activation energy, if I come here, we know that activation energy is just the minimum amount of energy that we require before the reaction actually commences. So activation energy is the minimum amount of energy, the minimum amount of energy required, the minimum amount of energy required for a reaction to commence or else for a reacting to start. To initiate a chemical reaction. So the activation energy is the minimum amount of energy required to initiate. To initiate means to start. To initiate means to start a chemical reaction. That is what we refer to as activation energy. Now they are now saying that a catalyst is now added to the reaction. Explain what a catalyst does and why it is added. So the main job of a catalyst is to speed up the rate of reaction. So that is the main reason of adding a what? A catalyst is to actually get to what? To speed up the rate of reaction. And how does the catalyst do that? It actually get to lower the activation energy. So the main job of the catalyst here is to lower the activation energy so that it can actually get to increase the rate of reaction. So your answer there for 4.6, you were just supposed to go and say that a catalyst lowers the activation energy of a chemical reaction. By doing this, it increases the rate of reaction. So a catalyst lowers the activation energy of a chemical reaction, thus increases the rate of reaction. So by lowering the activation energy, you are increasing the rate of reaction. Now they're saying, how does the catalyst influence the reverse reaction? So the catalyst will increase the rate of the reverse reaction, because that is the main purpose of a catalyst, to increase the rate. So it will increase the rate of the reverse reaction. That is the answer for that. Now redraw the graph to indicate the mechanism of how a catalyst will influence the reaction. Now it's more like they're saying redraw the graph when you now have got a catalyst. So when you now have got a catalyst, your reaction will now actually get to start here, and then it will go, and then so this is the actual reaction. But when you now have got a catalyst, we say that the catalyst, it lowers the activation energy. So maybe your activation energy now would come to be here. So we are saying that if our activation energy was equal to 60, maybe now it will come to something like around 40. So this is uncatalyzed, and this is when you have what? Catalyzed reaction. So you would have just drawn this potential time graph. So this one you'll be having what? Your potential energy in kilojoules, and then this one you'll be having what? Time, or else let me get to say progress of reaction. So here you would come and you say that this one is for uncatalyzed. And then this one is for what? This one is for a catalyzed reaction. So you would see that the activation energy has been lowered. Your activation energy there has been lowered. So this was the graph that you were supposed to draw for 4.8 there. That was the graph that you were supposed to draw. And that marks the end of question number 4. Let's go to question number 5. Question number 5, now it's now saying sulfuric acid is a strong acid, and that one we know, reacts with water in 2 steps as shown in the reactions below. And then they're saying what is meant by the term diprotic acid. So from what I have just read there, di means 2. Protic came from protons. So a diprotic acid, it's an acid that is actually going to have what? 2 protons. So you can actually get to say that an acid that can donate 2 protons, that's a diprotic what? Acid. An acid that can donate 2 protons. Because we know that from Bronsted-Lowry theory, so from the Bronsted-Lowry theory, an acid is defined as a proton donor. So if you now have got an acid that can donate 2 protons, then that acid becomes a diprotic acid. Now they're saying identify the ampholyte in the above reaction. What is an ampholyte? It's a substance that can either act as an acid or a base at the same time. Mean to say that in another reaction it's an acid, in another reaction it's a base. So we want to identify an ampholyte in these 2 reactions. So you can see that here sulfuric acid donates a proton to water, so that water becomes what? Hydrogen what? Sulfide. So you can actually get to see that this one, it's a base. So our water here is a base. And then we go to this reaction. Hydrogen sulfide also actually get to what? To donate a what? A proton here. No, yes. Hydrogen sulfide actually gets to donate a proton here, and then our sulfide, now this one is now a base, and then this one actually remains as a what? As a base. So now for us to identify our ampholyte there, it simply means that our ampholyte would become what? It will become what? H2SO4. Why are we saying that? At some point in time, H2SO4 will actually get to what? To donate, to actually get to remain with what? HSO4 minus. But in some instances, it can actually get to what? To receive. This can actually get to what? To receive, to actually get to form this, or else we can actually have what? H3SO4. At some point in time, you can react that and form that. So we would actually get to say that our ampholyte there becomes what? Our sulfuric acid. So it's just what? H2SO4 plus. So here you're just supposed to indicate that our ampholyte here, it's supposed to be what? H. Identify the ampholyte in the above equation. So you can actually get to see that at some point in time, this H3O plus is actually giving HSO4 minus a what? It is actually giving this one a proton, and then it becomes sulfuric acid here. And then at some point in time, you'll find that this sulfuric acid, at some point in time, you'll find that this HSO4 plus, it's actually donating what? It's donating and then remaining as a what? As a base. So let me just get to say, let's identify the easier one here. So I would come to say that we said an ampholyte can either become an acid at some point in time, or else it can become a base. So I'm saying that this one, you can see that this side, it's a base where it's receiving from H3O plus to become sulfuric acid. But here, this is actually donating. You can see that here it received to become this. Here it's donating to actually remain as that. And then this one is that. So you can actually come and then get to say HSO4 plus can actually become your what? Your ampholyte. It can receive when it is reacting with this, with H3O plus to become sulfuric acid. It can actually get to donate when it's reacting with water to become a sulfate. So this one becomes your ampholyte, because that is the substance that can actually act as a base or as an acid. Now 5.3, at some point in time, water also acts as what? As an ampholyte. But for that reaction, this one is the one that is ampholyte. I know someone would have said that, but I know that if you say HCl plus water, you would actually get to have your water acting as a base here, so that it received to become H3O plus, and then you are left with Cl minus. And then at some point in time, if you say what? If you actually come and say sodium hydroxide plus your water, you would actually get to have your what? You would actually have your sodium actually ending up with what? No, I wanted to say nitric acid here. I wanted to say nitric acid there. Maybe at some point in time, you would actually what? You would actually get to say what? Phosphoric acid. Yes, if you use what? Phosphoric acid there, you would have your what? Maybe let me just use this one to say that someone would have said that I know that this can actually be of that PO4. Since I have got that, this one would be minus. On this can actually end up being what? H3PO4. Whilst here, I'm having what? OH minus. Just like that. So water at some point in time can be your what? Your ampholyte. Whilst here, it is actually remaining as just a base. So the ampholyte that they wanted here, it was this one. That was the ampholyte that you can use there. So for 5.3, they were saying, write down any one of the conjugate acid-base pairs in the first reaction. Clearly identify the acid and base. Write down one of the conjugate acid-base pairs in the first reaction. So in the first reaction, let's identify our conjugate acid bases. So we know that each and every acid, according to Bromstead-Lowry theory, it actually carries, or else it has its one what? Conjugate base. So here, our sulfuric acid is our what? Is our acid. And then here, our sulfate becomes our what? our base, because here this one receives a proton to become an acid this side, but here this is the one that is donating. So here you would have what? H2SO4 being the acid, and then its conjugate base being HSO4 minus. That was for our first reaction. And then at some point in time, you would also have came and said, here I've got also a base which is water. So you would say, or you can choose either one of these. Or I've got my water acting as a base, and then that water, when it is this side, it's now the one that is donating. So here it's conjugate acid, so its conjugate acid becomes what? H3O plus. So you can choose either this pair or else that pair. That becomes the answer for this. So I'll take sulfuric acid, which is H2SO4, and then this becomes an acid. And then I would also get to take my conjugate base there to be what? To be HSO4 minus. So that becomes my conjugate base. So that would have become your what? That would have been your conjugate acid base pairs. So you can either take this or you can take that. So now let's go to give an example of any salt that will form with the acid in the second reaction. Any salt that will form with this. So this one is a sulphate and it's 2 minus. So any metal sulphate would be that what? It will be that salt. So I can either have my what? My calcium sulphate. I can either have my magnesium sulphate or else any metal sulphate. So it's either I take metal sulphate or else I take what? Magnesium sulphate. That would be my salt. Because all they want you to identify there is what makes your salt. So you would see that a metal and then a sulphate, they will form a what? A metal sulphate. And then that metal sulphate becomes a salt. A sulphate and a metal, they form what we refer to as a what? As a salt. So I can either have calcium sulphate, or else I can have magnesium sulphate, or else I can have copper sulphate. Can also have copper sulphate. They are all salts, those ones. And then now, so maybe you would have just said calcium sulphate, and then it becomes what? Your salt. Now, what color would bromothymol blue be if it is added to the second reaction, to this reaction? What is a bromothymol blue and what is its main purpose in this? So you see that this one, it's a pH indicator. This one is a pH indicator or else an acid base indicator. So this one is an acid base indicator. So it has got two colors. It is either yellow in acid or else it is blue in base solutions. So they are saying what color will bromothymol blue be if it is added to the second reaction. So to the second reaction here, you can see that this is acidic. So at some point in time, it will be what? It will be yellow. So you'll be having what? Your yellow color there, indicating the acidic solution of this. So here it was going to be what? It was going to be yellow. Because the main purpose of a bromothymol blue is to indicate either our solution is acidic or basic. So it will be yellow in acid and blue in base. And that solution of ours on reaction 2, it's acidic. So it was going to be yellow. Now let's go to question number 5.6. A solution of potassium hydroxide, is prepared by dissolving 3.36 grams of crystals of potassium hydroxide in 250 cubic meter solution. Now they are saying, is potassium hydroxide a weak or strong base? Explain your answer. We define strong bases or strong acids as those which completely ionizes. If a substance completely ionizes, in water, it becomes either a strong base or acid. It becomes either a strong base or what? Or acid. That is how we define strong base or acid. We need this to be completely ionizing. So we know that potassium hydroxide completely ionizes in water to actually get to form potassium ions and OH minus ions. So it is a strong base. And how would you explain your answer? You would simply get to say that potassium hydroxide completely ionizes in solution. So KOH is a strong base. It's a strong base because it ionizes completely. It ionizes completely in water. So anything that ionizes completely in water, it becomes a what? A strong base or acid. Now, calculate the concentration of the potassium hydroxide. Now we want the concentration of potassium hydroxide. Now, for us to find the concentration of the potassium hydroxide, we need to first find the number of moles, and then we later find the concentration. So we know that at some point in time, for you to find concentration, let me just get to move up. We know that concentration is equal to number of moles over volume. And then we know that the number of moles is equal to mass over molar mass. So we need the mass of what? We need the mass of potassium hydroxide and its molar mass. We are given what? 3.36 grams of potassium hydroxide. And what is the molar mass of potassium hydroxide? What is the molar mass of potassium hydroxide? We said that let's go back to our periodic table so that we can actually get to see our potassium. At some point in time, our potassium has got 39 atomic mass there. The atomic mass for potassium is 39. So if I want to find the molecular mass of potassium hydroxide, I will need to add 39 plus 16 for oxygen, and then I would add 1 for hydrogen. So this one would actually get to be equal to, so if I say 39 plus 16 plus 1, it is going to give me 56. So the molar mass for potassium hydroxide was going to be equal to 56 grams per mole. Now I just go back to our question so that we can be able to determine the number of moles there. So the number of moles here, we divide here by 56 grams per mole. And then our answer would be in moles. So if you say 3.3 divided by 56, you are going to get 0.06 moles. After getting the number of moles, I now need to find my concentration. My concentration would be 0.06 moles per unit volume that I have. What is the volume that I'm given for that? So they said calculate the concentration of potassium hydroxide. The volume that I was given for potassium hydroxide, it's what? It's 250 cubic centimeters. So this is the mass that I was given, and then this is the volume. So the volume there, you need to now get to convert it to decimeter cubed. We know that they are 1,000. So you would say divided by 250 over 1,000. So by divided by 1,000, you are converting to decimeter cubed. So this one would be a decimeter cubed. So your concentration was supposed to be equal to 0.24 moles per decimeter cubed. That was the concentration of what? Of potassium hydroxide. That was the concentration for potassium hydroxide. So this was the answer for 5.62. This was the answer for 5.62. So the concentration there was just supposed to be equal to 0.24 moles per decimeter cubed. And then now let's get to look into our following questions. So I would like you to allow me to rub everything here because we have already done this. So you are supposed to first find the number of moles of potassium hydroxide and then use the number of moles to calculate the concentration by saying number of moles divided by volume is equal to your concentration. Now let's hear the following questions. So here they are saying 25 cubic centimeters of potassium hydroxide solution of concentration 0.25 moles per decimeter cubed completely neutralizes a dilute solution of sulfuric acid in flask. The incomplete equation below represents the reaction that takes place. This is the incomplete equation, meaning to say that there is a missing product, which is D. That's why they are saying incomplete. Now, after that, let's hear what they are saying. Write down the name of the salt formed. What is the name of the salt formed? So this is the salt. So the name of this is just potassium sulphate. So it becomes what? Potassium sulphate. That is the name of the what? Of the salt formed. Potassium sulphate. So you know that if you neutralize an acid using a base, this is common. We know that you would form what? You would form a salt and water. So at some point in time, without being asked this, you need to know that this is what, because we have already formed a salt. That's why they're saying write down the name of the salt formed. So this is the salt formed, and then here we are going to form what? Now they're saying write down the formula of the compound D. The formula of compound D is just H2O, because that is what we are going to form. We are going to form water, and the water is just written as H2O. Now they're saying calculate the mass of sulfuric acid in the flask. Calculate the mass of the sulfuric acid in the flask. We are given what here? We are given the volume of potassium hydroxide. And then they are saying that the concentration is that neutralizing sulfuric acid completely. So we are saying that we need to what there? We need to what there? We need to actually get to calculate the number of moles of potassium hydroxide so that we can find the number of moles of sulfuric acid. Once we have the number of moles of sulfuric acid, we know the molecular mass, or else we can calculate the molecular mass of sulfuric acid. Then we can find the mass of sulfuric acid in the flask. So since sulfuric acid is reacting completely with potassium hydroxide, we can see that the molar ratio there is 2:1. So by first finding the number of moles of potassium hydroxide, we can be able to find the number of moles of sulfuric acid. So the number of moles of potassium hydroxide would be to say that we know that concentration is equal to number of moles over volume. So the number of moles there can be concentration times volume. For what? For potassium hydroxide. So this was going to be 0. What? It was going to be 0.02. I'm sure if you say 25 divided by 1000, you are going to get 0.02. 0.025 decimeter cubed times the volume. Sorry, this one was the volume times the concentration, which is that 0.25 moles per decimeter cubed. So if you, these ones, they will cancel out, and then you're going to get your answer in moles. So what is that? 0.025 times 0.25. You are going to get your answer as 0.00625. Once you have the number of moles of potassium hydroxide, you can actually get to find the number of moles of what? Sulfuric acid. So you see that sulfuric acid requires twice the number of moles of potassium hydroxide. So the number of moles that are going to react with this number of moles of potassium hydroxide are half. So the number of moles of sulfuric acid are just equal to what? To 1/2 times 0.00625 moles. And then by doing that, we're just supposed to find what? 0.003125 moles. These are the number of moles of sulfuric acid that is reacting. Now, how do we find the mass? We are doing 5.73. How do we find the mass? We know that mass is in relation to the number of moles by saying number of moles is equals to mass over molar mass. So we need to find the molar mass of what? Of sulfuric acid there, so that we can actually get to calculate the mass. So our mass was going to be number of moles times what? Molar mass of what? Of sulfuric acid. So we're going to say 0.03125 times the molar mass of sulfuric acid, that will be 2 plus 32, that becomes 34 plus 64, and then that was going to give us what? That was going to give us 98. So this is 98 grams per mole. So by doing that, you would actually get to say, you multiply by 98, you're supposed to find 0.3, you're supposed to find 0.31 grams by rounding off. So the mass of sulfuric acid was equal to what? 0.31 grams. That was the sulfuric acid which was in our flask because it reacted completely. Now let's do our last and final question, which is question number 6. Wow. Let's do question number 6. So question number 6 is saying that an investigation was done to determine the relationship between the pressure and the volume of a fixed mass of gas. The table below shows the results of the investigation. So these are the results of pressure and volume. Now they say use the results to draw a graph of volume versus pressure. So you are just supposed to come here, you draw a graph of what? Of your volume this side, because they said volume versus pressure in cubic centimeters. This was going to be your volume, and then your pressure this side, this was going to be in kilopascals. And then you can choose a scale for this side, you can choose a scale for that side, you can choose a scale for this side. So let's get to say maybe this was 1 centimeter, 1 centimeter, 1 centimeter, 1 centimeter, 1 centimeter. I was just going to choose a scale of what? For my pressure, I can see that the values, they're starting from 3.5 to 25. So I can use a scale of maybe, let me say 2.5, 2.5, 5, 7.5, and then I would have what? I would have 10, and then I would have maybe here I would have 12.5, I would have 15, 17.5. So let me just get to erase and use my scale correctly there. So here I would have chosen a scale that would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that it would say 2.5, 5, 7.5, 10, 12.5, 15, 17.5, 20, 22.5, and 25 kilopascals. So this is my pressure. So you would have just came represented your pressure here. And then for my volume, I'm starting from 5 to 35. I can also get to come and use maybe a scale of, let me just get to use a scale of 5. So 1 centimeter represented, 1 centimeter representing maybe 5 cubic centimeters. So I would come and say 5, 10, 15, 20, 25, 30, and then I would have 35 there. And then I start to plot 5 against 25. So it's 5 cubic centimeters against what? 25 kilopascal. That would be my first point there. And then I would plot 10 cubic centimeters against 12.5. So my 10 is here, and then my 12.5 is here. So I would have a value there. And then 20 against 6.25, 20 would be here, and 6.25 might actually be here. If I have my, let's get to say 6.25 there. And then for my 25 against 5, 25 against 5. So 25 against 5 would be somewhere around here. And then I would have 30 against 4.25. So this is 30 against somewhere like 4.25 here. And then I would have 35 against 3.5. 35 against 3.5. So mind you here, I'm just using a rough sketch to show you what we're supposed to do. So this graph would have gone as, I would join my points there, and then I was going to make a smooth curve up until there. So this was going to be my what? This was going to be my graph. But mind you, the graph here, was going to be a neat sketch. It was going to be a neat smooth curve. So this one was just supposed to be a smooth neat curve. So I used this just as an illustration of how you were going to draw this graph. You were just supposed to have your volume against your pressure. Choose a scale down here. Maybe let's get to say for pressure, you would get to say your scale. You just come and say scale, and then you say for pressure, 1 centimeter represents what? It represents 2.5 kilopascals. And then you would actually get to say for your volume, 1 centimeter would represent what? 5 cubic centimeters. And then after defining your scale, you will come and use this same scale to draw this graph. Mean to say that on your horizontal axis, 1 centimeter, this distance from here to there would be 1 centimeter to represent 2.5 pascals. After every 1 centimeter, you are representing what? 2.5 pascals. And then on your volume axis, which is your y-axis, 1 centimeter would be representing 5 cubic centimeters, 5 cubic centimeters, 5 cubic centimeters as you go. And then you plot these values to say this value of 25, which is this one, against this y value. That would be your point. And then 12.5, which is here, against 10, which is against your 10 here. And then you would say 6.25, which is this 6.25 here, against your what? Against your 20. And then you go 5, which is your 5, against your 25. So that is how you're plotting your points. And then you join those points on a smooth curve. And then now they're saying, which law describes the relationship between pressure and volume of a fixed amount of gas? So here we can see that your pressure varies inversely to the volume, or else your volume varies inversely to your pressure. You can see that as your volume is increasing, your pressure is what? Is decreasing. You can see that as I'm going up, my pressure is actually coming to what? To lower values. So as I'm also going to my right, my volume is actually decreasing. So this law is given by what? Or else who named this law? We know that this was Boyle's law, who said that if I get to have a confined gas with a fixed mass at the same or else at a constant temperature, my volume is going to vary inversely proportional to my what? To my pressure. So this one was what? Boyle's law. So that was the answer that you were supposed to state there for 6.2. So for 6.2, you were just going to say what? Boyle's law. That was for 2 marks. And then here they're saying, calculate the volume of the gas in cubic centimeters if the pressure exerted on the gas is what? 35 kilopascal. So now you are now using this law that you have stated above here. So what does that law say in terms of equations? You can actually get to state your Boyle's law, let me say 6.3, by saying P1 V1 is equals to what? P2 V2. So you can actually get to take any of these values. So I'll call this point 1. So if I have got what? If I have got 25 kilopascals, I will have a volume of what? 5 cubic centimeters. And then here they are saying, what about if I now have got a pressure of 35 kilopascals? What would be my volume? So I can divide throughout by what? By 35 kilopascals. And then divide throughout by 35 kilopascals. What is going to happen? I'm going to cancel these ones. So you are going to see that your volume here would necessarily be given by what? It will be equal to this divided by that. So by doing that, your volume was supposed to be equal to 3.57 cubic centimeters. So you see that these ones, they'll cancel out with thousands. I'll be left with cubic centimeters, and this will be my volume. So you can see that my pressure, so initially, let me get to say my initial condition where my pressure was 25 kilopascal and my volume was equal to what? 5 cubic centimeters. And then for my second condition, my pressure is now 35 kilopascals. Since my pressure is increased, my volume has to what? My volume has to decrease. That is the reason why my volume is now at 3.57. It has also decreased. This is due to that law. Now they are saying write down two conditions under which the gas used will behave like an ideal gas. So we know that for gases to start behaving like ideal gases, our pressure has to be low and our temperature has to be high. So under high temperatures and low pressures, so for 6.4, under high temperatures and under low pressures, this is where we are going to have a gas with zero volume, or else no what? No volume. And then the speed of the particles simply being constant, or else being the same. Having the same speed there. I can cancel out constant and say same. And also having no intermolecular forces. No intermolecular forces. So these are the assumptions that we make for ideal gases. We can only have this when our gas is under high temperature and low pressures. So for 6.4, you were just going to say high pressures and what? Low pressures. So that was our question paper, and it was out of 100 marks. Thank you guys, because this has been a long journey. Let's meet once again on our videos to come. Let's continue revising, guys. Let's continue reading, and let's continue to win. Let's meet in our next and following videos to come.